Okay, so before I get into the heart of my talk, just two things I want to bring up. One is I'm glad to see young people here tonight, because one thing I'd like to point out is when I was 13 years old, I started in my basement grinding my own telescope mirrors because I just loved astronomy. And that eventually turned into a 36-year career as being an optical engineer doing NASA missions for the most part. So you really can, if you love something, you really want to get into it, you can make a career out of it. And I've had a great career. I've been so lucky. And the second thing is sort of related to that, and that is I want to thank you all because for the last 36 years, you paid my salary. And you've allowed me to do these really cool things. And one of the things I feel important to me as both an amateur astronomer, a lifelong amateur astronomer, and working on these NASA missions, is it's really important for me to give back and for me to say, hey, I've done this. I've done some really cool things in my career, and talking to astronomy clubs with people who have a similar love to me of astronomy, I just absolutely enjoy doing. So I'm happy to, drive up here a couple hours from Maryland, and I'm glad I do it every time. So let's get going. I am the type of person who, like squirrel, and I go off that way. So feel free to ask me questions, and who knows where we'll end up. And I'm fine doing that. So we'll talk about New Horizons a little bit itself. I'm going to spend probably almost half the talk talking about how you build space instruments. I'll try not to go too technical, but like I said, if you guys see a technical thread you want to pull, go ahead and pull that, and I'll try to answer the questions. I'll show you science images from Jupiter, because we did fly by Jupiter for a gravity assist, and we took science data there, and a lot from Pluto. And then we're going to talk about the encounter we're having next January 1st with a Kuiper Belt object, a small Kuiper Belt object. So please don't invite me to any of your New Year's Eve parties, because I can't go this year. And actually, the encounter starts on Christmas Day, so my family already knows this will be the first Christmas I don't spend with my family. Okay, mission background. You guys all know that we flew by Pluto and Sharon in July of 2015. We're going to go by this Kuiper Belt object this year. We're the first of the New Frontiers class missions. We were launched in January '06. Where I work at Johns Hopkins University Applied Physics Laboratory, we built the spacecraft, and we built two of the instruments, including my instrument, Lorri. And we're about 2 astronomical units from the Kuiper Belt object right now. I think we're at about 40 AU right now. So what's that, 3 billion miles or 4 billion miles? I forget. 4 billion, I guess. Optical instruments on New Horizons. We have 3 optical instruments. We have also other particle instruments and things of that sort. I know nothing about those. So if you ask me a question about that, you'll get a deer in the headlights look. So we have the Alice instrument, which is an FUV spectrometer. I spent the first 20 years of my career building FUV spectrometers, so I do know a lot about that. We have the Ralph instrument. So the color images you've seen are mostly from Ralph, and that also has an infrared spectrometer on it. So Alice is mainly to look at atmosphere, to see light coming and glowing in the atmosphere, identifying atmospheric constituents. Ralph is more to look at chemicals on the surface of Pluto or whatever we're going by. And Lorri, my instrument, is basically just a really long focal length telephoto lens. So you can take the highest resolution images we can take. And of course, Lorri will be the focus of this talk. So where are we right now? That shows you where we've been and all. You can see Mars and Earth way in the middle there. And we swung around, hit Jupiter. And I'll point out that since we went by Jupiter, Jupiter was, well, I'll go over here. Jupiter was here when we did our gravitational assist in 2007. Since then, Jupiter's gone all the way around us, almost all the way back around, right? It was a 12-year orbit. So we launched in January '06, near perfect trajectory, fastest Earth departure ever. What are we, 36,000 miles per hour. We were by the moon in 9 hours. Remember the Apollo missions, for those in my age group, what did it take, 2.5 days or something for the Apollo astronauts to get there? We were by Mars in less than 3 months. Most Mars missions take 9 months or something to get there. Of course, they have to stop. We just went flying by. Here's all the instruments. So we have the Alice spectrometer. It's about yay big. Ralph, which is right next to it there, the color imager. Where that came from. There's the radio experiment where we actually use our communications dish to receive radio waves broadcast from the big dishes on Earth, going through the atmosphere of Pluto and Sharon, for example. We have on the bottom right the student dust counter. So that's a big plate of metal that is actually in the direction New Horizons is going most of the time. And when little particles of dust hit it, we count each one of those. So from Earth all the way out past Pluto, we've been counting dust particles in the solar system, which is really cool new science. There are the two particulate instruments, PEPSI and SWAP, solar, wind, and energetic particles, and that's all I know about them. And then mine on the bottom left there. New Horizons looks like this, or looks like that, with that beautiful model you guys have in the back there. Important to point out here, all of the instruments you see on New Horizons. So Ralph, Alice, the two particle instruments, student dust counters underneath. It's a big telescope inside New Horizons looking out. And that'll be an important point in a few minutes that I'm going to get to. What makes us different? Again, there's all the instruments. This is one of my favorite shots putting it together. This is at our clean room at Johns Hopkins, putting the communications dish on. But you can see Lorri inside the spacecraft right here. So here's the spacecraft. Is that going through? Yeah, good. With one side removed, where you see the black there, the side is off it. And you can see this tube sticking out here, right there, with a bag on the end, and that's the Lorri telescope. So that's the instrument I worked on. So New Horizons is generally described about being the size of a grand piano and sort of the shape a little bit. It's actually a little bit thicker than I think a typical grand piano is, and probably a little bit, that's probably actually in the same weight category. All right, so you're going to build a science instrument. The first thing you got to do is decide what it has to do. So you come up with a list of requirements, and it's usually the science team that comes up with this. So for the Lorri instrument, the scientists got together and they told us engineers what we need to do. So they wanted us to collect images before we arrived at Pluto, about 90 days out, that were about the resolution as you could get with the Hubble Space Telescope on Earth. I don't know if you've ever seen the pictures that Hubble takes of Pluto. They're about 12 pixels across. They show a darker area and a lighter area, but they're not overly satisfying. So they said, we want those quality images about 90 days out. They want us to collect images of the hemisphere that we don't go by at closest approach. So remember, Pluto has an orbital period. Pluto and Sharon together have a period of about 6.2 days. We go by Pluto in a few hours. I'll show you a chart later that shows you how quick we went by those two. So 3 days beforehand is the last best chance you get to see that part you're not going to fly by real closely. So they asked us to collect images of that hemisphere at approximately 40-kilometer resolutions. That means that each of our little pixels on Lorri is about 40 kilometers across. They also wanted us to obtain the highest resolution panchromatic. Panchromatic just means monochrome, like old black and white camera. Images at closest approach. So what they wanted is about 100 meters per pixel. We actually ended up with about 70 meters per pixel. And they wanted good signal to noise ratio. That means satisfying images, images that don't look grainy. So we had to have a large enough aperture to do that. We needed to obtain navigation images. So as we're approaching Pluto and we're approaching the Kuiper Belt object that we're going to get to this year, we need to know where it is so we can use our thrusters so we go by at just the right point. So all our pre-planned pictures, and everything's pre-planned way in advance. We're already running our test runs right now of what we're going to do in January. So going by the object you're going by at the right distance is really critical in order to get the images you intended to get. So we needed to obtain navigation images, meaning we can see this very faint Kuiper Belt object we're coming to, for example, well in advance of getting there. So those of you who are big into astronomy, that's magnitude 17 in a 10-second exposure. That's a really faint star. We ended up with an instrument that looks like this. So telescope aperture is 208 millimeters, that's about 8 inches. The focal length is 2.5 meters, a little over 2.5 meters. So that's a slow telephoto lens. If you're a photographer, it's f13. Field of view is about 1/3 of a degree squared. It's kind of like looking through a soda straw. It's a really narrow field of view. Pixel field of view, each pixel is an arc second. And the wavelength range is basically visible light. So we're gonna count every bit of visible light we can get. And we're just a 1 megapixel. For those of you who deal megapixels, we're only a 1 megapixel camera. And our exposure times are typically fairly short. They're of order 100 milliseconds, so 1/10 of a second. And the reason for that is we don't have reaction wheels on New Horizons. We don't have wheels to stabilize us so we can point at, you know, a planet and just stay there. We use our thrusters and we point, and then when we start drifting off a little bit, we pulse the thrusters and move back the other way, and we sort of are rocking. So we want to take short exposure times because of that. That's what the optical layout looks like. So you got a hyperbolic mirror on the right side, another one that's convex on the left side, and then it goes down to a focal plane there and it has some field flattening lenses. This is full scale of the guts of Lorri. It's a 3D model we had printed. I'll pass it around. Just don't pick it up by this, even though I just did it. Pick it up by these things. But that's full scale. Okay, so I said that the thing that's different about Lorri is we're inside the spacecraft. All the other instruments are hanging off the outside. They have the advantage of controlling their own environment. So they can be hanging off the spacecraft, they can wrap themselves in a blanket and put a heater there and be at exactly whatever temperature they want. Lorri, on the other hand, is inside a room temperature spacecraft. So just exactly the same temperature right now. Even though they're in deep space, they've got the waste heat from their generator that's heating the whole spacecraft. But we're looking out a hole in the side of it at deep space, right? So if we're looking at deep space, we're looking at 3 kelvins, right, which is minus 400 and some degrees Fahrenheit. So we're looking at Pluto, we're looking at 40 kelvins, so we're looking at minus 350 degrees Fahrenheit. So we're looking at really cold stuff. And the back side of our camera, right, that's the front side of the camera, the back side of the camera has a focal plane that we need to keep cold as well. So it doesn't have what's called dark current. So we keep that at about minus 80, minus 90 Celsius. I'm switching units like crazy on you because that's what engineers do. So that's, I don't know, minus 100 and some. So you got really cold out front, you got something really cold in the back, and you got this tube in between that's trying to be room temperature. So those of you who are into amateur astronomy, that's a recipe for bad focus, right? You're gonna, those of you who, there's a few of you here I know who do astrophotography, what do? You have your telescope out and you let it get to the temperature of the outside before you start taking your pictures, because it's gonna wanna defocus. So we're flying this thing, it's gonna wanna defocus, and we don't put a focus mechanism on, so we don't have one of those knobs like you have on the back of your telescope to focus it. We have no way to focus it. So we've set ourselves up for having a really tough environment to get the best images we can get. So we need to think about how we can prevent Lorri from going out of focus. And the way you can think of doing that is the materials you pick. So you can pick a telescope that's made out of a material that doesn't shrink and grow much with heating up or cooling down, right? That's called thermal, coefficient of thermal expansion, CTE. So if you make a telescope out of materials that don't change much with temperature, that'll want to stay in focus better. So you could pick a material like, there's special glasses called like Zero Dur or Cital and things like that, that basically don't expand and contract with temperature at all. So that would be one option, but then you have to make your whole telescope out of that, including not just your mirrors, but what's in between it. So it all expands and contracts the same little bit or not at all. The other way you get around it is you build it out of a material that moves heat very quickly. So think of like aluminum or copper, that if you heat up one side, it makes the other side real hot, real quick. So what that does is it minimizes the temperature difference from one end to the other. So you can go either of those paths. The problem until the last 20 or so years has been there aren't many materials that have both of those properties. So we were one of the first civilian instruments that used a material called silicon carbide that has both those properties. It doesn't have quite zero expansion, it has very low expansion, and it moves heat very well. So it's minimizing the temperature difference from front to back, and what little difference is left doesn't change much. Does that make sense? So we went to a company up in Massachusetts that specializes in that, and what you guys are passing around right there, almost everything you're holding in real life is made out of the silicon carbide material, which is like a ceramic. If you were holding it, you'd say, oh, this is a piece of ceramic. So that's, all the instruments I built in my career, this is probably the easiest one. It doesn't have a lot of mechanisms and all, but the one big trick was having it not expand and contract much. Our design, we could deal with about a 4 or 5 degree Fahrenheit temperature difference one end to the other. We ended up with less than 1 degree. So we have very good focus. I think I've covered all of this. Yep. So we at APL designed and built the electronics. We designed the overall Lorri system. We had the company in Massachusetts build the optics for us. We put it back all together and then we qualified it. I'm going to spend quite a few minutes, well, 5 or 10 minutes talking about qualification. Here's what it looks like, the gray part in the middle there. So in here is what you guys are passing around right now. The mirrors are, of course, coated with aluminum. So they're very shiny. They don't look ceramic like the rest of it does. It has a large baffle going out here, made out of composite, so like hockey stick, tennis stick material. Very biggest rocket we could buy and launch the lightest payload we could go to, and then we can get to Pluto fastest. That was the whole idea behind it. We have an electronics box that controls the camera. We have a radiator here with a conducting bar that goes down. And remember I said I had to keep the camera chip cold? That's how we move the heat out. There's a piece of beryllium and then we radiate that to deep space. So it's all passive. We're just cooling passively. Piece you're just passing around looks like that in real life. You can see, nice gray color. You can see the mirror has a nice aluminum coating on it. If you look down the baffle, it looks like this. You can see the spider veins. So imagine now that the part the little girl has back there is in the middle looking at you. And the baffle veins are to keep stray light from entering into your field of view. Then there's a lens assembly at the back that flattens out the focal plane. Okay, our little piece of silicon that we detect the light with is perfectly flat. This type of telescope wants to create a field that's curved, like bowl-shaped. So if you didn't flatten the field, you'd end up with just a ring of best focus rather than a whole field of best focus. So you put a couple of lenses in the back to flatten out the field. This is what the focal plane, the thing that actually detects the light, looks like. So this little black area here, it's about the size of a postage stamp. That's where the business is done. That's where the photons of light strike that silicon and get converted to electrons. And then we just read that out into the electronics into a 1,000 by 1,000 array, basically, to get the images out. There's a flexible piece of electronic wiring here that allows us to keep the focal plane here at the minus 100 or so F I told you about earlier, while at the same time this electronics board here is mounted to the spacecraft and is running at room temperature. So that very thin piece of copper there transmits very little heat between the two, and that's why that's there. Then the focal plane gets mounted on the back here underneath, and we move the heat out up this conducting bar. It's a piece of beryllium, very light piece of metal, but very highly conductive. And there's a link here, a flex link, which is 400 or so layers of very thin aluminum foil that are all sandwiched together, and that way it doesn't transmit the loads from the spacecraft to the instrument. You don't put the instrument out of focus by bending it. It's sort of like, reminds me of a slinky type thing. So you can imagine a slinky, you could move around one side and it doesn't really affect the other side much, so you're not moving things and changing the alignment of things. There's what it looks like on the bench. So we have ground support equipment that we use. This is a piece of ground support equipment that imitates the spacecraft, and we're just cantilevered off. We're hanging off the wall of the spacecraft, so this piece imitates the spacecraft for us. We've got, there it is, graphite epoxy, or no, better, let me call it fiberglass legs that go up. They transmit very little heat. They're very insulating. So the spacecraft here, again, is at room temperature, and the whole telescope is actually running at minus 100 F or so. So we can't move much heat in, and those legs prevent that. There's the brains of the unit. We have a computer. There's a power supply, and there's an interface for the camera, all in this little box that's about this big. And then the other way we keep it uniform in temperature is we wrap it in blankets. So typically on spacecraft, you wrap things in blankets to keep them warm, to keep the heat in. In Lorri's case, we're wrapping it with blankets to keep the heat out. So these are, I don't know, 15 layers of mylar, very thin mylar with mesh in between. So they transmit very, very little heat from the spacecraft into Lorri. So one thing we have to do when you're working with optics for space is you need to keep them very, very clean. If you don't, you end up losing light because you get films on your mirrors or lenses, sort of like the film you get on your car windshield, you know, on the hot days on the inside. So when that happens, you have more scattered light in your photographs and you also lose light. And then also just dust creates little shadows on your image that you have to correct for. So dust is bad, and molecular contamination, the inside of your windshield stuff, is also bad. So how you deal with that is you work in a clean room. So you put everything together in a clean room. So all the hardware going into your instrument has to be precision clean, and there's people who do this for a living, just clean spacecraft hardware. So they clean it, they'll put it in a bag, put that in another bag, and then they'll put that in storage until we're ready to use it. And then we'll all go into this clean room, which has a large moving air and these huge filters, and blow, you're in, like being on wind tunnels too much, but you're in a gentle breeze all the time. And you, the person, is the biggest contaminator in the clean room. So what do? We wrap you up. So we wear complete coveralls all the way top to bottom. We wear a hood, we wear boots, mask, gloves, and sometimes you even have to wear 2 layers of gloves, and you're peeling off the outer layers all the time and replacing them. The big thing about working in a clean room is it really slows down your progress. Because, imagine that 10 o'clock in the morning and I really need a cup of coffee. If I'm going out for coffee, I need to take all my stuff off. I need to go out, get the coffee. I need to finish it. I can't take it back in the clean room. Put all my stuff back in, and back in I go. So probably, I don't want to say it doubles how long it takes you to do a typical thing, but it probably is at least 50% more time to do things when you're working in a clean room. So here's what one of our clean rooms looks like. Typical clean rooms are all white, so you can tell if there's dirt. But we're doing optical work. We don't want light scattering, bouncing off the walls, so we want everything black. This clean room I was working in, the ceiling was black, the walls were black, the floor was black, the optical bench was black, and it was about 20 feet by 15 feet, and trust me, after 12 hours a day in there, you're close to losing your sanity. So Lorri in here on this bench is here looking out in this direction. We have a mirror here, and we have something called a collimator here. A collimator is just a telescope working backwards. So instead of having a camera where the telescope comes to a focus, you put a light where it comes to a focus. It spreads the light back out and makes it look like it's coming from infinity. So this way I can focus a telescope in a clean room and know that when I look at a star that really is way far away, or Pluto that's 10,000 kilometers away from us, that will be in focus. So that's how we do our focus. We also do something called flat fields. Probably there's 3 or 4 people in here who do imaging, astronomy. They know what I'm talking about. But you have to, in order to get rid of those dust shadows I talked about, which we call dust donuts, you have to know where the dust donuts are. So what you do is you just light up a white sheet, and you take a picture of a white sheet, and then you use that to process your later images to take out those artifacts. We also do spend a lot of time doing environmental testing. So we put an instrument together, we check it electrically, make sure it's working, and we make sure it's in focus and all that good stuff. And then we try to break it on the ground. You say, why in the world would you want to do that? Well, you want it to break on the ground if it's going to break. So you need to test it in the environments it's going to see when it launches. So what does it say, right? It goes on the launch pad. You basically set off this huge bomb underneath it that makes it go up in the air. And that whole time it's launching, it's vibrating like crazy. Okay, so imagine you got my computer here. If I took up my computer and I just go like that with it, it might break the computer, right? The other thing you get when you're on a rocket is a lot of noise. The sound, anybody go to the Cape or Wallops and see a launch and you just feel that sound pressure on your sternum and all? There's a huge amount of sound energy when you're on a rocket being launched. So if you have things that are, big plain things that are thin, they'll act like a drum head, right? And they'll beat back and forth. So the sound energy can actually break things. So you have that, and then once you get into space, space is very cold, right? We're looking out at space, and I told you it was like 3K or whatever, very cold. And you're in vacuum. And then also you're dealing with the electronics around you, and electronics can have noise. You've seen interference, those of you who remember old days TV, right, when you get the interference on the TV. So they're the things you have to think about beforehand. So what do? We put it on a table, and we shake it back and forth. And we shake it to higher levels than it'll shake on the rocket. And then we put it in a special room that has huge speakers, and we play Led Zeppelin but we play very, very loud noise that, again, is louder than the rocket's going to produce. And the whole time, we're running our instrument. We're looking, is there anything glitching? Is it still working? Yada, yada, yada. We make it through those things. Then we put it in a big vacuum chamber that has a liquid nitrogen shroud all around it, so we can cool it down to space-like temperatures. And we'll cool it down and vacuum and warm it up and cool it down, and we'll do that like at least a half a dozen times. Again, we're trying to exercise it. We don't want it to break, but if it breaks, we want it to break on the ground when we can fix it. And then we also measure how much electrical noise it generates, and then we also put it in an environment where we put electrical noise on it and make sure it still works. So that's environmental testing, and that's a huge part of the work I do, that I've been doing my whole career. And by the way, for Lorri, we tested at the box level. We put it together in an instrument. We went through all these tests again at an instrument level, and then it went on to spacecraft and went through all those tests again at the instrument level, at spacecraft level. So 3 times it went through all these environments. Here's an example. This is one of those vibration tables I told you about. So this is a table that goes up and down, pistons like this. So Lorri is in a bag right here. Actually, it's in 2 bags, because the room we were doing our vibration in wasn't a clean room, so we had to keep Lorri clean for this. So we put 2 bags around it, and that little line you see coming up from the bottom is a purge line. So we're blowing very clean, dry nitrogen in to keep it clean while it's doing this. So this test would start with what's called a sine sweep usually. So you do this little sine motions, and they keep getting finer, and you keep going faster and faster and faster. You look how it reacts. And then you randomly vibrate it, and then you do a sine sweep again, and you see if it changed, because the changes would tell you if you broke something. Then you go in a thermal vac chamber. And typically you just put your instrument in a thermal vacuum chamber with a liquid nitrogen shroud around it, but Lorri's different again. Lorri is inside a warm spacecraft. So we sort of had to build a fake spacecraft around Lorri, and that's what that box is, with Lorri sticking out the front. It's very much like Lorri is on New Horizons, and we can keep the outside there at room temperature in simulating the spacecraft, or we can turn it off and cool it down and give it the thermal cycles we need to give it to exercise it. We also have to calibrate an optical instrument. So we need to put it at temperature in a vacuum and make sure it's still in focus, and know when we put a certain amount of light in, we get a certain amount of counts out. So we know how efficient Lorri is at converting photons into electrical signals that we interpret as images. So our calibration setup, we had a big vacuum chamber, which I'll show you in a second. We had, again, a collimator, something to make it look like we're sending it light from infinity, with a light source behind it that shoots light into Lorri. We measure how much light we're shooting in. We know how well in focus that simulated light going in is. Well, not simulated light, but simulated infinity is. And we compare our images. That's the vacuum chamber we're in. This is a chamber that you actually lift the top off of. And you go up the steps, so you actually just walk around in the vacuum chamber to set up your equipment. There's a collimator, so this is basically at the telescope working in reverse. And these were collimators we actually had built for a different mission 10, 15 years earlier, and we repurposed them again for Lorri, and they work very well for that. We put it on a gimbal so we can tilt and pan, so we can put the simulated image in and make the simulated image look like it's in the center of the field or one of the corners, and make sure that the performance is uniform over the whole field of view. We put Lorri in a liquid nitrogen shroud to control its temperature. That's what that silver mass is and the hoses going around. That's environmental testing. Anybody have any questions? You guys haven't interrupted me much yet. I've had a lot of caffeine tonight.
Ever break Lorri?
Say again?
You ever break Lorri?
No, actually we were amazingly successful, just amazingly. And I've been through, for example, vibration tests where we were doing some stuff for the space shuttle. This is 30-some years ago, where literally a pump fell off, and one of the scientists I was with had to catch it. That was a very bad Saturday for us. Anybody else? Was there somebody back there? Yeah?
Yeah, that was sort of the question I was going to ask. The one that you subject to all that testing is the one that you launched?
Oh yeah, yeah. We do Protoflight. So Protoflight means that we build the unit. The first full unit we build is the one that we fly. So we actually have to test that a little more rigorously than if we had a prototype on the ground that we test very rigorously and then build another one to fly.
Where do you gain the confidence that that will survive a second barrage of testing?
Well, you do a lot of analysis before you ever go in a test situation. So you already know you've got significant margins of safety on all of your design before you go in. And then you're testing at a level much below that. And plus, as we said, we test 3 times, right? So all our boxes are tested as boxes, then we test as an instrument, and then we test on the spacecraft. So yeah, at some point, it's an imperfect system, right? Anybody else? Yeah.
So my understanding then the biggest stress for the Lorri is during the takeoff.
Yes.
Do you have some kind of test after that takeoff to understand whether it's working or not?
Oh yeah, yeah. So so we launched in January. In August, we got to the point where we believed that the contamination on the spacecraft would have been outgassed into space. So we opened our door at that point, and we just looked at a star, and the star field we looked at was in really good focus.
And what was the plan if it's not working?
The one nice thing we had on New Horizons was Lorri was a Class 2 instrument, so we could go. We could do all of the science requirements for New Horizons without Lorri.
So it would still go, the mission
We would have still had a very successful mission, but we wouldn't have some of the really nice high resolution images we ended up with. Anybody else? Sir?
How long would it take from concept to putting it onto the launch?
I was involved with the proposal in the winter of 2000, 2001, and we delivered to the spacecraft our instrument in November 2004. And after you do your proposal, you have to wait for the proposal to be accepted and all that stuff. So there's probably almost a year of empty time in there. So it's probably about 2 years to make Lorri and put it on the spacecraft. And then it was a little over a year to go through spacecraft level testing and go to the launch pad and all.
Sorry, one more question. You mentioned that the highest resolution of images were monochromatic.
Yep.
What is the reason for that?
Our requirements did not require us to be color, okay? So if we were to make a color imager, it would be a lot more costly and it would weigh more. So we said, here's how many dollars you have, here's how many kilograms you have, and here's what it needs to do. There were points where we said, oh man, it would have been so nice if Lorri had been color. But it worked, it did what it was supposed to do. We made our requirements, we were on budget, and we were on time.
Is that the same reason why you did 1 meg?
Well, part of the reason for that is spaceflight qualified stuff is hard to get. That's why you always look and you say, boy, why are their processors so small? Why are their imagers so small? Well, oftentimes we're using hardware that's been made 8, 10 years ago because it has to get space qualified, and it costs so much to qualify stuff for space that you can't always have the latest and greatest. You have to have something that you know will work. Anybody else? Okay, so here we are putting Lorri on the spacecraft in November '04. I'm in the lower left there. Big mistake to have somebody with my little wimpy arms holding a large value instrument for what seemed like forever while they put the 3 screws in. Okay, so now that gets us up to the encounters. So we went by Jupiter. The reason we went by Jupiter, we had to fly on time and all, is to get the gravitational assist and get to Pluto a few years early. So that was #1 reason. #2 reason for Jupiter is to learn how to use our instruments. And no, #3 is if you can get some science data, that would be great. So this shows you flying by. I think each one of these ticks is every 10 hours. It shows you where the moons were when we flew by. And you see that little tiny bend in Lorri's trajectory, and that's the gravitational assist. And what do we pick up? 10,000 miles per hour, 10,000 miles per hour just going by Jupiter. Just a couple of pictures we took there that are kind of cool, in my opinion, as an amateur astronomer. The little red spot, we did movies. And movies is probably an overstatement. We took an image and waited 20 minutes, take another image, wait 20 minutes, etc. And doing that, we were able to measure how fast the winds in the little red spot of Jupiter are. You could see we had almost measures of 400-mile-an-hour winds. And what is that, a Category 8 hurricane or something like that? Not real typical here on Earth. My personal favorites of Jupiter are the Io volcano shots. So here are the sulfur volcanoes on the moon Io, shooting sulfur hundreds of kilometers above the surface and then raining back down onto the surface. And the cool pictures like this are coming down over the terminator, so you can see it's still in the light of the sun as it rains down on the dark side of Io. And the back side of Io is just lit up by the light of Jupiter itself. Any questions on Jupiter before we go on to Pluto? Okay, so first thing you need to remember about Pluto, or know about Pluto, is the rotation of the moons is not in plane with the ecliptic. So it's not in plane with the rest of the planets in the solar system. It's more like on a 60-degree angle. So if you were to make little maps of the moons going around Pluto, they'd look like you're coming in on a dartboard on an angle. So here is the dots. Remember Jupiter a minute ago, each dot on this trajectories were 10 hours. Here they're 10 minutes. So you can see, 11 o'clock we were here, 12 o'clock we were there, 1 o'clock in the afternoon we were there. So the whole heart of the encounter period was depending on how you look, 6 hours or so. Yes, sir.
What's the communication time to Pluto?
When we were at Pluto, I believe it was about a 9-hour round trip light time. Okay, so you threw me my squirrel thing here. So New Horizons was the first time in my life that the speed of light really affected my life. You know, you saw the Apollo mission in a few seconds to talk to the Earth and between Earth and Moon and all. So we launched New Horizons, and like I said, in August, was that 8 months after or so we launched, we went to open the door of my instrument. And we did that by a ground command. You know, oftentimes we will upload command, or most of the time we upload command sequences to the spacecraft to say, at 2 o'clock do this, at 2:05 do that, da 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 da. Well, this is, we tell it on the ground, okay, open the door now, and they hit the return key. The command goes down the road from where I work in Laurel, Maryland, to the Goddard Space Flight Center down in Greenbelt, Maryland. It then goes up to a satellite, gets relayed back down to Australia to a 70-meter dish in Australia, and then that's pointed at New Horizons, and that command goes up. So at that time, I think it was about almost a 1-hour round-trip light time. Maybe it was 45 minutes or something like that. But as soon as you hit that return, and that the signal went down to Australia and left that antenna in Australia, it's still 20-some minutes before your door starts to open. But if I was to suddenly say, oh my gosh, I really don't want to open my door, there's nothing in the world I can do about it. And you know, it's like, what is it, Schrodinger's cat or whatever? You know, I don't know if my door is going to open for the next 45 minutes, and there's nothing in the world I can do about it. So it was a very, very strange situation. And you know, now when we do tests, if I do a test that requires real commands, and we're almost 12 hours round trip light time now, you know, I can almost do one thing on one shift, go home, sleep, and come back, and then get the results. So this shows you our trajectory coming in at that dartboard. And we were required to fly in the shadow of Pluto and the shadow of Sharon. We did that so both the Alice instrument could see the shadow of the atmosphere from the sun going through the atmosphere, so we could look for elements in the atmosphere. And we were also being shadowed by the Earth, or shadowed by Pluto to the Earth, so we could look with our radio dish at energy being broadcast from those 70-meter dishes on the Earth, as that was attenuated by the atmosphere as well. That tells you a lot about the atmospheric properties. So we had to time our mission to go through both those shadows. When we launched, we only knew about Sharon. We didn't know about the other 4 moons. So that's why you look and you say, well, look, why did you guys go by when Hydra was so far from you? Because Hydra's like one of the really cool looking moons. It's the one that kind of looks like a little ducky, rubber ducky. And the reason why those pictures are so coarse is because unfortunately Hydra was as far as it could possibly be from us when we went by. But we really couldn't adjust that timing and have everything else work. So that's why we got what we got. So I told you we opened my door in August '06, and of course what's the first thing we do when we start playing for real is, well, let's take a picture of Pluto now. So that's a picture of Pluto when we're still 30 AU, so almost the distance that Earth is typically to Pluto. And what does it look like? Well, it looks like a dot. So if I was to go in my backyard observatory and take a picture of Pluto, it would look pretty much like that. And then we fast forward to July of 13, and we can finally now see Sharon, right? Now remember, we're looking with an 8-inch telescope. Sharon was discovered with I think a 36-inch telescope or something like that. Maybe somebody else knows better than I do, from Earth. So now we're 6 AU, so what we've gone about 80% of the way to Pluto, and now we can finally see Sharon with my telescope. And then we go to April of 15, and now you can finally start seeing some, there it goes, some of the structure on Pluto, and that's pretty comparable to Hubble images at the time, what you see zoomed in on the bottom there. The other thing I really like about this image is you see Pluto and Sharon rotating about their barycenter. So think of it as sort of like center of mass. And you can see, it's outside. So Pluto's doing these little circles, and Sharon's doing the big circle all around that same point. And then in May, we finally see Kerberos and Styx, the two smallest moons. And this one doesn't run very well, unfortunately. There's the original image. Then we subtract out all the background stars, and that's where the other two images are. And then you see them going around. So about that time, well, actually about a month later, we had another Styx sighting, which was this. So the rock band Styx turned out to be giving a show down in Virginia, and they said, hey, we hear these NASA rocket scientists who are looking for a moon with our name. So I'm only kidding. They were actually really good guys and all. And they came up and they visited our operations center. And I'll also point out, there's other rock and roll fans here, that Brian May from Queen, who was, I guess, the guitarist with Queen, he's also an astrophysicist, and he was actually part of our team during the encounter. And he was really very, very knowledgeable guy, scary guy. All right, that gets us up to June. Now we're, I don't know, 2 Pluto rotation periods from closest encounter. We're starting to get really intriguing looking images. And you're saying, holy cow, how come he's got color in a Lorri image? Well, what we do is Ralph, the color imager, has lower resolution, so we take their color and we paint it on our high resolution images. And that's how you get images that look like this. And you can see some of the features that, were informally named, like you can see the head of the whale here coming around, and the tail would be coming next. And then the holes are what I thought of as like bowling ball holes on the other side. So it shows you the two opposite hemispheres. And, Sharon, Pluto's showing you how bright it is at its north pole, right? And its north pole is about here. And then the similar north pole on Sharon is there, and how dark that is. So being an amateur astronomer, getting to be among the first people in the world to see these images when I would wake up at 3 in the morning to do my engineering checks was a real privilege. It was really exciting every day when we got new images now. And then again, here's adding the images. So we have the high resolution reflectance map from Lorri on the left. We have the color image from Ralph on the right, and we merge them together in the middle to get those color images. Then this is, remember I said we had to get 40-kilometer resolution 3 days out to get what I always refer to as the backside of Pluto, though there, of course, is no backside. And so this is our last image of the spots and the polygons and all that you could see on Pluto. Was just astounding. And then, even Sharon by itself was just very cool to see, the chasm going across the middle, impact craters, which seems to have more in Sharon than on Pluto, the dark polar region. Then we had the image we released the day of closest encounter, which again is another colorized version. We took the high resolution Lorri and painted the Ralph color on it. If you want to be entertained, you can probably still find the article from Science Magazine online about making this image overnight and the excitement the scientists had putting this image together. I also really am a big fan of the XKCD Comic. If you want to look up this one and actually read all the things, the different names, informal names he came up with for different surface features. Certainly he was a big fan of our mission, and we were featured several times in his comic. Then you start looking at the area between the plains and the mountains on Pluto, and the level of contrast was just amazing when you get areas that are white as snow or nearly as white as snow, and then areas that are as black as charcoal that are near each other. That's a factor of 10 on the amount of light that's coming off of those areas. Then And then you get this amazingly complex view of Sharon with the, the crack-like area that goes all the way across the middle that they think might be because of the middle freezing and the outside cracking as it expanded. The family of moons, and this is to scale. So you see the edge of Sharon on the bottom there. And these are some of our best images. Now, Nix was the one we were closest to. That's why you see the images much more satisfyingly there. Kerberos and Styx were, a few pixels across each. And Hydra, I really would have loved to get better pictures of just because it has such an intriguing shape. The objects or features like this possible ice volcano that they found. So imagine this is, 5 or 10,000 feet tall and has what looks like a cauldron in the middle of it. My personal favorite is the pond, or what I call the pond. And when this got downlinked when I was on a trip for another program, I was out in Oklahoma, but I was checking my images on a Sunday as they were coming down into fall of 15. And this came down, and I got on the phone to my scientist I work for, and I said, Hal, it looks like a pond. He said, well, it's a dried one, but just the fact that Pluto has features like this to me is just, completely astounding. And then the atmospheric haze. One requirement we didn't have on New Horizons was nobody ever told me you need to look back into the sun 12 degrees off the sun. So that's like trying to take an image near that light, of the ceiling, the dark ceiling. It'd be really hard to do. You're going to get a lot of scattered light in. But there was no harm in trying, and when we tried, we got amazing photographs of the hazy atmosphere looking back in. When you process those, this is the original image, and then this is processed, you can see how many layers there are in that atmosphere. Okay, that was Pluto. And how am I doing on time? Doing good?
You're fine.
I'm fine, okay. That's a first. Like I said, the caffeine really helped tonight. Any questions on Pluto before I talk about what we're doing in January this year?
So what is actually made for? Is it like mostly ice? Or
It's ice and rock, yeah. But the ice on the surface, the water ice on the surface is so cold, it has more properties of rock than ice. It's really very strong, and the mountains that are as high as the Rocky Mountains, are mainly out of ice. And the ice is strong enough to hold because it's that cold. And then the other ices, like the nitrogen ice and the carbon monoxide ice, are more slushy. And that's why they think there are glaciers and things like that that are moving. That's, is Pluto still alive? And it looks like it may be as far as geologic activity goes. Anybody else? Okay, so we're not done yet. After we went by Pluto, well, let me start a little bit before that. So when we told NASA we were doing this mission, we said, oh, we're going to go by Pluto and Sharon, and then we're going to discover 1 or 2 other Kuiper Belt objects that will have enough fuel left to just move our spacecraft a little bit off the original course and fly by 1 or 2 other objects. So we said, oh, we'll find the objects after we launch. And we started looking, the scientists, not me, started looking using some of the big telescopes on Earth, and we really didn't find any. And we kept looking and looking, and by 2014, we had asked for time on Hubble, to use Hubble to look at that area of space, because Hubble can see deeper than anything on Earth can, and see if they could find some Kuiper Belt objects for us. They were able to find 3 candidate objects. Well, they actually found 6, but only 3 we could reach with our fuel. So we had to decide between those 3 objects. We couldn't go to more than 1 just because of how they were oriented. One of them would have taken almost all our fuel, so we decided not to go there. The other one would have taken a significant amount, but was a little bit bigger. And the one we decided to go for took very little fuel, but was smaller. Or I shouldn't say necessarily smaller, less bright to Hubble, okay? So they found that in 2014. It's completely unresolved to Hubble. What does that mean? That means it's a pixel. It's one bright spot. So all you know is it's this bright. You don't know how big it is. You don't know what the shape is. But we knew where it was. We've never been able to see it directly from the ground. You know, they determined, okay, when are we going to fly by it? We know roughly how far it is out, and they came up with January 1st of this coming year. Decided we're going to fly by about 3,000 kilometers. We flew by Pluto at about 11,000 and change, so we're going 3 or 4 times closer. So you're going to get better resolved images, but of course it's a much smaller object. So Kuiper Belt objects can be high or low albedo. Albedo is, you know, is it very dark like that wall over there, or is it very bright like this wall? So high albedo, low albedo. Imagine now Hubble's looking at this, it only sees it as a point. If it's really dark, if it's as dark as that black wall there, it could be really big. If it's bright as this wall, it could be really small and you get the same amount of light. You can't tell the difference, right? So all we could say was, based on the Hubble data, it's somewhere between 10 kilometers across, what's that, like 6 miles, 7 miles, or 40, so 25 miles. But that's all we knew. You know, you couldn't do any better from Earth, because those of you who are amateur astronomers, you know, it's 1,000th of an arc second in size. So that's looking at an orange 20,000 kilometers or 13,000 miles away. You know, what does an orange look like from that far away? So you're not going to get any more data from the Earth doing that. So what does that mean for our encounter? If Ultima Thule, as they've nicknamed it, or MU69, is white like this and small, it's going to be like the left side there. So imagine it's circular. That's the field of view of my instrument at 3,000 kilometers. So if we knew exactly where it was going by and we knew it was that size, we could take one image and we're done. Of course, we would never do that, but we get the whole thing. On the other hand, if it's dark like that wall, it could be 40 kilometers across. You could see, we'd take one image and we'd miss most of it. So we'd have to do a pattern where you go across and took 9 images in order to get the whole thing, right? So it would be really nice if we knew how big it was. We'd also like to know what shape it is. So there are a lot of, in that size category, there are a lot of unusually shaped asteroids, for example, or comet nuclei. You know, here's an example of asteroid Eros that looks like a banana with chunks out of it. And there's also objects like Centaur objects that have rings, like Saturn does. So you'd really like to know in advance if it has rings or is unusually shaped. So again, so you can plan the pictures you're going to take as you go by. And also, you wouldn't want to fly through a ring, right? Because you might hit something. So they sent us down to Argentina to measure this from the ground using amateur telescopes, believe it or not. And the way we did that was we did an occultation. We waited for the Kuiper Belt object to go in front of a star and blink that star out for a few seconds. And if you have a whole bunch of telescopes lined up and down a line waiting for the star to blink out, you hope that a few of them get the blink out, and when they do, you know how long it blinked out, you know where you were on Earth, you can get a silhouette of the object. So even though you can't see the object, you can determine how big it is and what the rough size is. So they sent us down to Argentina twice to do this, and this is where my background as an amateur astronomer who as a hobby measures asteroids using this technique came in, and it was like, Steve, do you want to take a vacation down to Argentina on us? And myself and 12 other amateurs went, as well as about 30 or 40 professional astronomers. What we came up with is this. So we got 5 chords across it, 5 lines across the body. And you can say, take those 5 endpoints and you can draw anything that goes through those. And oh, you can't go through the bottom gray line, so it can't have crossed that line, can't have crossed that line. Connect the dots, and what shape do you come up with? So speculation is it 2 bodies? Is it what's called a contact binary? So 2 things that have merged together and now are rotating about, you know, in contact. Was it 2 things that are just closely rotating by each other and we happened to catch them when they were slightly overlapping? Or is it just, you know, an odd-shaped object, which it could well be? What do we know? We know it's We know how big it is. It's 30 kilometers by 15 kilometers, and we know it's not circular. So it's going to look really cool. That I promise you. So, you know, an artist comes up with a contact binary, like on the left there, or an odd-shaped object, like on the right. And then we found one more thing. We actually did 3 of these occultations where we looked for the stars to blink out as the object went across. The ones we did the first time up here, we missed it. That's what these lines are, with no breaks in them. The ones here, with these breaks here, here, are the ones we did the second time in Argentina. And then we had the Sophia airplane with the big telescope, the 2.5 meter telescope, and then a 747, go over the Pacific and look for one of these in the middle of July of last year. And they just saw this tiny, tiny little blink for one frame. And they assumed, well, you usually don't judge things based on one frame of data. But then somebody looked and they said, but we expected MU69 to be right here. And hey, if you draw a line from this guy to this guy, that's right along that line. So could it be just sort of like the Pluto situation where there's a barycenter here, center of rotation there, and this guy's rotating here and these guys are rotating there? So maybe there's another object there. We don't know. We're going to find out. Okay, real quick, other uses for Lorri. They started, a year or two ago, we started looking at distant Kuiper Belt objects. So when we go by these objects that are a couple astronomical units away from us, we're taking images of them to see how bright they are because we're looking at a side view. So, you know, imagine that light is the sun. When we're at Earth looking at a Kuiper Belt object, we're always looking from right around the sun. We're always looking with light coming down and bouncing straight back. When Lorri's going by, we're like over here. So we can get light that comes down and scatters this way. If you take the ratio of light you see looking like this versus the light you see like this, you can tell a lot about the surface properties. So even though it's still only a pixel across, you can start learning how rough it is or what the materials may be. And they've also used Lorri to come up with a limit for background light in the solar system. Solar system, in the inner solar system where we are, there's a lot of dust particles that create something called zodiacal light, light that is reflected off those dust particles and comes back. We're so far out now that we get very little of that, so we can look at the background light in the universe and get a measure of that. So we're going to also pursue that. I'm also starting to work on the next Lorri. So the Lucy mission was selected a year or so ago to be the next discovery mission. We're going to go to the Jupiter Trojan asteroids. So we're going to go to the asteroids that lead Jupiter in its orbit by 60 degrees and the ones that trail Jupiter by 60 degrees. We're going to visit both those and use a Lorri instrument to take images of those. And that one's called L Lorri or Lucy Lorri. And that'll launch in 2021. I think that's all I've got for my slides. Just my acknowledgments. Happy to take any questions you have. Yeah, sir.
What was the duration when you were with the team of astronomers measuring the occultation? What was the total duration of that period?
Second and a half.
Second and a half.
Yeah, so we were imaging at 5 hertz. So basically, you know, for the longest one, the star blinked out for 7 or 8 exposures.
And it was a composite of all the people imaging together?
So for that one, we had people for 100 miles up and down the coastal highway of Argentina at minus 46 degrees latitude in the middle of winter in the city that's called the Queen of the Winds, where the wind was always blowing 25 miles an hour. The biggest problem we had was shielding our telescopes from the wind. I was lucky and unlucky. I was the furthest south station, and we were on the beach, and trust me, it wasn't the time of year to be on the beach. But we were lucky enough we found an old industrial crane from World War II that had toppled over, and the framework was sitting there. So we put tarps all around this framework and put a telescope inside, and we were sheltered from the wind. Or at least I was, because the other 2 guys wasn't enough room for them inside, and I was the one inside.
Has that process ever been done before? Is that the first time? Sounds like interferometry, but visibly?
We do it all the time on asteroids. So we've been doing it for 20 or 30 years. I'm happy to give a talk to you guys on it sometime. Yeah.
As you get closer, at some point, will you be able to get like a tiny little image of the Kuiper Belt object?
Oh, we'll get an image that'll be a very nice image, very well resolved image. But that's a good point to bring up, though. For those of you who really followed along with New Horizons, you know, starting, like I said, three or so months out, you started seeing images being released in the news media, you know, and they got bigger. And then a week later, you'd see another image that was bigger, and oh, this is going to be so cool. And then 2 weeks later, it was even better. You're not going to get this time. This is going to look like a dot on my imager until the last day. So, you know, the last day, it's going to go from a dot to filling up my whole imager, and I'm going to have to take a mosaic. I'm going to have to take several pictures to get the whole thing. So you're not going to get that buildup. You're not going to get the first really good images until a couple of days later when we downlink the first ones. That doesn't mean anything's wrong. That's exactly what's supposed to happen. Yes?
What is the bandwidth between New Horizon and, you know, as far as transmitting those images back to Earth?
A little under 3,000 bits per second. So it's very much like your old modem. In fact, we were just saying at dinner tonight, I really wish they had the sound of the modem, you know.
So does that affect, you know, the resolution of our, you know, the acceptable resolution of our imager?
Well,
if you have a very large resolution, you know, it takes too much time to bring.
Yeah, and that's a trade-off. That's an absolute trade-off. If you had more pixels, you would downlink less things.
Are there any images that were not transmitted yet just because?
Nope. There is no, we transmitted every single image, even if it was dark sky, because maybe there was something else there. Maybe there was a small satellite we didn't know about. Yeah.
What's next after that?
For me personally,
For New Horizons.
New Horizons we'll have enough fuel to take science data, I think, to 2028, and then we'll either run out of fuel and our generator will lose power. You know, we're down to, I forgot, 185 watts or something right now. That's our whole power. So, you know, 2 of these lights is our entire power, and our broadcasting back to Earth is about 10 watts. So,
What's the source of energy?
radioisotope thermal generator, or RTG. So, some plutonium that is hot. Yeah.
If you have an issue of you don't really know what your field of view is yet, and your lead time your turnaround time is so long getting there and getting back, how are you going to know whether just to take that single shot or do the mosaic?
Oh, we're doing a mosaic. Yeah. Yeah. We're
regardless of which. Okay.
Yeah, but it affects our planning. But you know, we've already got every picture planned out. And in fact, right now as we speak, we are doing a test run of the 13 days of closest approach on a electrical version of a satellite in a electronics lab back at APL. And next week, I'm going to look at all that data and make sure we took 4,000 images, and every one of the 4,000 images looked correct and was at the right time and all that stuff. So we do runs like that over and over again because we got one shot that's got to be perfect.
Now, you said it's going to run until
2028 or so.
Are you still going to attempt to grab some more images after?
Well, we have to get an extension on our extended mission. So that's NASA will say, is it worth the money to make this happen? Is the science compelling enough to pay for it? And that's something that they have to decide because, of course, we have an opinion, right?
At this point, you're going to be the furthest thing into space at this point, right?
Oh, no. We'll never catch up with the Voyagers.
Oh, the Voyagers, right?
Yeah, they're more than twice as far as we are. But then again, they were launched when I was in high school. Anybody else? Well, it's great talking to you all tonight. If you want to come up and ask me any questions, I'm happy to do that.
Thank you.